Our objective in this video is to learn how to solve radical equations by graphing. They can also be solved algebraically, but we want to make sure that we also can graph and check whether we have no solution, one solution, or two solutions, so that our algebraic answers can match our graphing answers. Okay, so before we start talking about radical equations, we're going to just I'm going to remind you how to solve by graphing. So the first thing I want you to do is try to think about how you would solve this equation algebraically. So if I ask you to solve this equation, you would subtract 2, and then you would divide by 3, and this will give you an answer of x is equal to -2. So a couple of things I want to point out is that we're going to get a solution that looks like x equals a number, and also if you check your answer, you can confirm that it's correct because you can take that -2, you can substitute it into the left side to get an answer, and confirm that it's equal to the right side. So if you never solved by graphing, this could be something new to you. But one way that we can solve this is we can break up our equation and think of it as two different functions. So one equation is going to be y is equal to 3x plus 2, which is a line with a y-intercept of 2 and a slope of positive 3. So we go up 3 over 1. And then we also have another line where the equation is y is equal to -4. So this is an equation of a line where y is always -4, so that's why it's like this, it's a horizontal line. And we're looking for a place where both y values are the same, and our solution is going to be the x value that makes it happen. So we're looking for the intersection point, which is right here. So the y is the answer that we get on both sides. So this is the -4 equals to -4. That's our y value. And the x that we got, which is -2, oops, sorry, this is pretty bad. Okay. So the x value that we get is our actual answer because that's what makes our left side equal to -4 and our right side is equal to -4. So I guess the general approach would be to take your equation, break it up into the left side and the right side equation, graph them separately, look for the intersection point, and then once you find it, you can look for the x coordinate of the intersection point because that's going to be your answer since you're looking for the x. Alright, so here's our first example where we actually apply this method to solving radical equations. So my equation is 3 square root of x is equal to 6. So what I'm going to do is I'm going to graph 3 square root of x first, and this is going to be a square root of x function that is stretched by 3. So instead of at 1, 1, it's going to be at 1, 3, and instead of at 4, 2, it's going to be at 4, 4. And I'm going to do one more, so if it's at 9, it's going to be at 6. Oh, it's not going to be at 6. And this is going to be, sorry. Okay, it's going to be 3 as far. So 4 is usually at 2, so now it's going to be at 6. And 9 is usually, square root of 9 is usually 3, but we triple it, so it's going to be here. So that looks a lot better. Alright, so our equation is going to be looking like this. So this is my left side of the equation, and then I also have another equation, y equals 6, which is a horizontal line, where y is always 6, and our solution is going to be the x value of the intersection point, which happens at 4. And the y value of the intersection point is basically going to be the y value of the left side and the right side once we substitute in the 4. So this will be 3 square root of 4 is equal to 6. 3 times 2 is 6. So this is saying the y value at x equals 4 is 6 for both equations, and that's why they intersect. Alright, so here's another one for us. We have a radical function that is shifted right 6 units, so it starts here, and we're going to go up 1 over 1, and for 2. And then we also have a linear equation that is y equals x, so it has a slope of 1 and a y-intercept of 1. It's just, a y-intercept of 0. So I have to be a little careful here because it's not 1 by 1 boxes. So up 1 over 1, up 1 over 1. If you notice, the y's go, the boxes in the y directions are half units away from each other. Alright, so hopefully you notice that what's going to happen is that they never are going to intersect, because this is going up faster than this radical equation, and they're really far away from each other. So no matter where we go, they're never going to intersect. So this would have a no solution. So this equation has no solution because they don't intersect. Alright, so this is the first problem that I want you to do by yourself. So pause the video, try to graph this, and see if you can solve it. Alright, so this is what my graph looks like. So this is my y equals square root of x plus 7 plus 5, which is the left side. And my y equals 9 is right here, so it's my right side. So my solution is going to be the x value of the intersection. And they intersect at 9, so that's my solution. And what I'm going to do is I'm going to double check by substituting the 9 into my equation. So first I'm going to check the left side. And my right side is 9, so 9 plus 7 is 16, so square root of 16 plus 5. And I get 4 plus 5, which is 9, and it works out. And remember that the 9 is the y value that we get on the left for the left equation and the right equation, and that's why they intersect. Alright, so here's another one. We're going to pause the video and we're going to try this on our own. Alright, so I graphed both functions, and this is what my graphs look like. They intersect at x equals 7. So that looks like it's my solution. And what I'm going to do is I'm going to check that it actually works out. Because usually on the graphs, this looks pretty good, but sometimes it's not. It might be off a little bit, so whenever you solve graphically and you do it by hand, it's usually a good idea to double check. If you're using graphing calculator, then you don't have to double check. And this looks great. Alright, we get 2 equals 2, and the 2 is the y value that you get. So this is saying when x is 7, you get y 2 on the left and 2 on the right, and this is our y value. Alright, so here's another example, so we're going to pause and do it on our own. Alright, so here's an interesting graph for you. They intersect in one point right here where the blue graph starts, and then they clearly don't intersect again because this one is increasing and this one is decreasing. And they intersect at x is equal to 1, and that's our solution. And what we're going to do is we're going to double check. We're going to substitute the 1 into the left and to the right part of the equation just to make sure that it works out. So we get 2 minus 2 is equal to 0, and 0 is equal to 0, and 0 is our y value here. So that's where we're getting it from. Alright, this is our last one, so hopefully we get this right, and we can continue with our lesson. Alright, so this is our last problem, and we get the two graphs to intersect at one point that has the x coordinate of x equals 3, which is going to be our solution. and we're going to double check, and we're going to plug it into the left and into the right. And we get square root of 1 is equal to 1, which is correct. And 1 is our y value here that we get. So that's the end of the lesson. Couple things to talk about really quickly. This is just a method to get solutions by graphing. Even if you don't, even if you're not asked to solve by graphing, this could be a really good method to double check that the number of solutions that you're getting is making sense. So for example, sometimes if you solve algebraically, you get extraneous solutions, which are extra solutions that don't actually work. And you have to double check each one. But if you graph, and let's say you see that you have two graphs that look like that, and clearly they don't intersect, that tells you that there is no solution. It's possible for you to have one intersection like we had in our problem. We had one like this. We had another problem where we had two radical equations and they intersected in one place. So you can have one solution. And you can also have two solutions, which we didn't have in any of our problems, but it's definitely possible. So for two solutions, you can have a radical equation that has a graph, and you have a linear equation that has a graph that intersects the radical function in two places. So you can have something like this, or you can also have a radical function that's probably a bad one. So you can have a radical function that starts here and maybe it goes up, and then eventually they would intersect, something like that. So it's definitely possible to have two solutions, no solution, or one solution. And if you're not sure algebraically how many you have, you can definitely double check using graphing. And it doesn't have to be perfect, but you could just sketch it quickly if you're familiar with graphing, and double check whether the number of your solutions makes sense.